We got work out of the way. We've talked about that. Now we're going to broaden our understanding of energy so we can kind of add a few things. Now, in our problems, we're going to have kinetic, potential, and internal energy. Now, we haven't seen internal energy before. That's probably going to be something new you haven't seen in another class yet. Internal energy is going to account for all other kinds of energy changes. Okay, so these changes are typically going to be found in a table. Okay, or you'll be asked to solve for them. All right, so we don't necessarily have like the 1/2 mv squared equation for internal energy. Okay, so in order to go over how we're going to put all this together, all three different types of energy, let's look from step 1 to step 2 of a process. And let's look at the energy. So E2 is going to be our total energy, and let's subtract that from E1. So that's our change in total energy as we do this process. Now that's going to equal the change in internal energy. These are capital U's. You want to make sure you didn't denote in your notes that those are capital U's because that will matter later on. Okay, so we got U2 minus U1. This is the change in internal energy. So U's will always be internal energy. And then after that, we're going to add to that the difference in kinetic energy. So we'll have our kinetic energy at state 2 subtracted with the kinetic energy at state 1. And then finally, you guessed it, we got potential energy. So here we're going to have the potential energy at state 2 minus potential energy at state 1. So these are going to be our three energy sources we're going to have in this equation. So put it all together, gives you your total energy change. Okay, now another way to write that is delta E equals delta capital U plus delta KE plus delta PE. All right. So this is going to be an equation we're going to be using. We're going to add it to something else in just a second. So now that we've got that down and we know that equation, let's talk about energy transfer by heat. Okay, so we're going to have an energy transfer by heat that's going to be caused by a temperature difference between the system and its surroundings. Okay. So think about if you have a piston cylinder assembly and you put it in a really hot environment, what's going to happen to that gas inside that cylinder? Unless it is really, really, really insulated, that gas inside that cylinder is going to heat up. Okay, so you're going to have an energy transfer by heat, and it's going to be caused by that temperature difference. Okay, now energy transfers are only going to occur in the direction of decreasing temperature. So what does that mean? That means it's always going to go from hot to cold. So the cold body will warm up. All right, you're not ever going to get heat or energy transferred from the cold body to the hot body. It just doesn't work that way. Okay, so it's always hot to cold. So this is going to be important. And we'll talk about it again later on in the course. Now we're going to have a sign convention and notation for heat transfer. The symbol we're going to use for heat transfer is going to be Q right here. So capital Q. Capital Q is going to be the amount of energy that's transferred across the boundary of a system in a heat interaction with the system's surrounding. Okay, so that's what we'll have. So Q, anytime you got heat transfer or energy that's moved around because of a temperature difference, we're going to have that Q term. Now we've got a sign convention that goes with this. And this is going to be one of those important things, just like the sign convention with work. So when Q is greater than 0, that means heat transfers to the system. And when Q is less than 0, heat transfers from the system. So to and from are your keywords there. And again, make note of that because you'll be using that sign convention quite a bit. So let's think about what this is saying. So if heat is transferring to the system, then that probably means, let's just draw a little cylinder here, that means that it's going to be really hot in the surroundings. It's going to be a lot hotter in the surroundings than it is in this gas. So heat is going to come in here, and that's going to be Q. All right, so you got energy transferring into your system if Q is positive. Now, if heat is transferring from the system, then in this case, we draw our little cylinder. In this case, the gas in here, for example, would be a lot hotter than the surroundings. So we're going to have a Q out. Okay, so this again is arrows showing the direction of heat transfer on your figures. So sometimes you'll just have an arrow, and that's what it'll look like. So if it's going into the system, that's going to be a positive Q. If it's going out, negative Q. Okay, now that we have that done, our rate of heat transfer is going to be Q dot. So remember that dot just indicates a rate. And we can get Q from that because Q is the integral from T1 to T2 of Q dot dt. So this would give you the amount of heat transfer during a time interval. And that time interval would obviously be T2 minus T1. Okay. Now there's also something else you can use, and this is called heat flux. So we can use heat flux, which is a little q dot, to find Q dot. Right? So let's write down what Q dot is, this little q dot, because you might not know what heat flux is. So little q dot, what that is, that's the heat transfer rate per unit of system surface area. Okay, so that's all little q dot is. So it's just basically your rate per a surface area. And the mathematical equation for that, you could say Q dot is equal to the integral over the area of little q dot times dA. Okay? And we're not really going to use this equation in this course, but that's what it is if you care to look at it. Okay. Now, next, what we've got is a term that we need to look at, and this is going to be one of the keywords we want to pay attention to. And this term is adiabatic. Okay? So adiabatic, what does that mean? We're going to have an adiabatic process if the system undergoes a process with no heat transfer. All right, so no heat transfer. Adiabatic means no heat transfer. Okay? And that's going to be important to look for this term when you're working out your problems, because if you see where it says the system is undergoing an adiabatic process, that means Q is going to be 0. Okay, because there's no heat transfer. So keyword right here, make sure you pay attention to that one, because we will see it over and over and over again. Okay? All right, guys. So let's stop there before this video gets too long, and we'll pick up in the next video. See y'all then.